Hi students, I'm the Doc, and this is Practical Science. Hi students, welcome to Practical Science. Today we're going to have a look at both colorimetry and also a way of quantitatively calculating an equilibrium constant. We're going to use chemicals we've used previously, and we're going to recreate the iron thiocyanate equilibrium, and we're going to see if we can create some different solutions, measure their absorbance with different wavelengths of light, create a calibration curve or a line, and then to see if we can create an unknown solution, and from the absorbance calculate its concentration, and then see if we can work out an equilibrium constant. So today we're going to combine some of these magnificent pieces from the Tiny Science Lab along with some Pasco gear which I have purchased from Cider House. And we're looking at a colorimeter today. So I've already calibrated that, so I need to calibrate that first of all. And we're also going to be giving you a little bit of a look at some of the output that we're going to get from each of the different solutions that we put together. So I'm going to need to use cuvettes, and the cuvettes are going to have each different solution in them. But in order to make sure that I don't confuse myself, I'm just going to number these cuvettes first of all. So I'm going to put the numbers 1, 2, 3, and 4. So the first thing that we need to do is we need to create our calibration curve. In order to do that, we need to have a little bit of an idea of what the actual concentrations for the different solutions are. Now the challenge with this is that we have an equilibrium system that we're looking at. And the idea of an equilibrium system is that we have both products and reactants present, and we don't push the reaction to completion. Now I'm going to kind of break that rule a little bit by using such a large amount of one of the reactants that I effectively react almost all of the other reactant. And so therefore I can use that concentration in order to calculate my concentration of the product, which in this case is iron thiocyanate. So I'm going to be starting with a 1 molar solution of iron nitrate. So you can see the color is quite dark. And I'm going to be mixing that with a 0.01 molar solution of potassium thiocyanate. So with these two together, hopefully this one is a 100 times more concentrated solution than this one. And so hopefully that will push the equilibrium far enough that we will effectively have pushed it right to the edge. So I'm going to get my measuring cylinder out. And the first thing I'm going to do now, you'll notice that I have 4 cuvettes here, 1, 2, 3, 4. And what I've done is I've written down a different sequence combination for each of these solutions. So I'm going to start my first solution, and I'm going to use 0.5 mils of my potassium thiocyanate, and I'm going to combine that with 2 mils of my iron nitrate. So let me do each of these first of all. Now what I want to do with each of these solutions is I want to make them up to 4 mils in total, so all of the solutions have the same final volume. So I'm going to add some distilled water to get myself to my final volume of 4 mils. You can see that classic red color, and that is our iron thiocyanate. So what I'll do is just mix those together. And that what we'll do is this is solution number 1, so I'm going to now transfer this solution to cuvette number 1. You have to make sure that there's enough in the cuvette so that when the light passes through it, it's actually passing through solution. Let's pop this on the cuvette, the lid, and now let's see what we get. And there's a beautiful look at the absorbance in each of the different wavelengths of light. So you can see not much of the red's absorbed, large amount of the violet and the blue have absorbed. So we've got some nice values there, and we're just going to repeat that for each of the 4 solutions. In order to create our calibration curve, what we need to do is we need to measure the absorbance of each of these. And having had a look at our initial results, I've decided that we're going to go with the green light. So we'll look at the absorbance values here. So one of the advantages of using the Pasco colorimeters is there's actually a function in here where you can do exactly the same thing and record all the absorbances, but this time you can actually have it plot the line for you based on the values that it puts in. The only difference here is that you need to make sure that you do the calculation of the concentrations beforehand, because obviously if it's trying to draw a graph, it needs to have two data points at each stage. So I've now got some nice values that are coming up here for my solutions. So let me try the fourth one, pop that in there, and those are, then I'm going to have some really nice values, and you'll see that we have a calibration curve, and that's what we can use to then work out the concentration of our unknown solutions. So you can see all of the absorbance is going up. This makes sense to me because I'm assuming that the concentration is also going up based on the amounts of each of the solutions that's in there. So I kept the same volume of my iron nitrate, but I increased the volume of my potassium thiocyanate in order to see if I could continue to push the amount of iron thiocyanate that was being produced. So that's what's produced this beautiful red color, and by increasing the concentration I should expect more absorbance, and that is what I see. The thing that you might notice about this is that the graph is reasonably straight, but it looks like one of these values is a little bit of an outlier, and that could have just been experimental error, the way that I measured things. We are dealing with very small quantities here, which means that we need to make sure that we're very, very accurate in what we do. Otherwise, small differences can be magnified and have large effects when we're looking at our calibration curves. But this isn't too bad. Okay, so now it's time to mark up our actual equilibrium mixture. So what we're going to do this time is we're going to add some of the same concentration of the potassium thiocyanate that we've used before, which is 0.01 molar. So I'm going to again grab 2 mils of that, but this time I'm going to drop the concentration of the iron nitrate. So I'm now going to be using a 0.001 molar solution. The color is very faint. There's not very many ions in there. Well, actually there's a very large number. It's just that they're comparatively to the water not as high, and therefore they don't follow the water to the same extent. So let's have a look and see what sort of result we can get. And again, we're going to use 2 mils. So we have a total of 4 mils, which has been our yardstick all the way through. So you can see the color. We'll give that a little bit of a mix. And then, as we've done previously, we will transfer that into our cuvette, and we will measure its absorbance. Turn this on. Just before I do that, let's just calibrate it. Let's double check the calibration. Good. And now we'll take that out of there, and we'll put this one in. And you can see now that we've got a value of 0.091. So it's a much lower absorbance, and we would expect that because the concentration of ions is much lower, and therefore not as many ions will be available to absorb the green wavelength of light, the 550 nanometer wavelengths of green light. And so as a result, we've got a much lower value, and that means that we're able to now use our calibration line to work out what the actual concentration of iron thiocyanate ions are in this solution. And from there, we can calculate the equilibrium constant. So before we do the final calculations, there's probably a couple of things that we need to recognize. Firstly, the errors associated with the collection of values and then the construction of the calibration curve are significant. And you can see that from the fact that if I use the line of best fit that passes through all my data points, I calculate a value of concentration which is almost twice what I would get if I bring that line back to the origin. However, because the absorbance value is so low, I have to have a line that passes through the origin in order to make sense out of the data that I have. I can't construct anything that's logical if I don't. And what that does is it increases the amount of error associated with this particular experiment. Nevertheless, we're going to push ahead and at least work through the calculations so that you have some idea of how to process this information. The most important thing, of course, is repetition. And even with the last step, I only carried that out once. It's obviously a good idea to carry it out a couple of times. Reflecting on this particular experiment, one of the things that I would do differently next time is I would definitely change my initial concentrations. I think I needed to have a smaller concentration, a 0.001 concentration of my potassium thiocyanate to begin with, in order to construct my calibration curve in the first place. I think the fact that I started with a higher concentration meant that I had some very high absorbance values, and it was much more difficult for me to get those high values back towards the origin without skewing my line in some ways. But we've got some numbers, so let's see what we would do with these. So of course, the first thing that I'm always going to do when I start this process is I'm going to write down the equation, because that's always an important start. So we've got iron ions, thiocyanate ions, and they're in equilibrium with iron thiocyanate, which is our red colored solution. Okay, now I do have potassium ions and nitrate ions in the solution as well, but they are spectator ions. Now, one of the reasons that I do this is because I'm always interested in my mole ratios. And one of the reasons this is such a popular one, you can find heaps and heaps of different methods, and you can vary what I've looked at today to whatever method suits you really. But the nice thing about this equilibrium is it produces 1:1:1 ratios. So when we look at our ice tables, that makes life a little easier. The calculations that we've used in order to get us to our concentrations for the calibration curves are simply a function of C1V1 equals C2V2. So I kind of alluded to that earlier in the video, but you can have a look at that in a little bit more detail. So for example, for the calibration step, if one of my values was, say, a 1 mil of SCN minus ions, and I wanted to know what the concentration of FeSCN2 plus was, then I use the concentration, which I said was 0.01. I multiply that by the 1 mil. I'm going to leave that as 1 at the moment, and then I'm going to divide that by the total volume, which was 4 mils. And that's why I've left these as mils, because if I change them to litres, the multiplication factors will cancel out, and so then I'll still have 1 on 4. It's just going to be 0.001 divided by 0.004. So in this case, I get a concentration of 0.0025 mole per litre. So this is how I did the calculation for the concentrations, and then obviously we plotted those against the absorbance values. We got a series of data points, and then we drew our line of best fit. And unfortunately, our line of best fit did not seem to pass through the origin, and that's why we had to extrapolate that down. We had to take it to values beyond those that we used in order to give us a line which was sensible, mainly because the value that we had for the absorbance was so low that it would have actually ended up with some sort of negative value. So that was not going to be great. So what we're in a position to do now is by finding this value here on our x-axis, we know what the concentration, or at least the equilibrium concentration of the iron thiocyanate is. So what I'm going to do now is I'm going to set up my ice table. So my ice table is going to be number of moles initially, number of moles that changed, and the number of moles at equilibrium. And remember, it's the change that relates to the mole ratio. So how does it change? It changes through a chemical reaction, and so the chemical reaction has to obey those mole ratios. So they're the ones that are going to be consistent. Now I will also have in my table the volume at equilibrium. Now in this case, this is 4 mils, so I made sure that my final volume was 4 mils. And obviously all of the ions are in the same solution, so they're all going to be 4 mils, but I am going to turn this into litres this time around because I'm not going to cancel things out, and so therefore I'll be out. So 0.004, so the volume for all of the ions at equilibrium is the same. Now it's the concentration at equilibrium that I need for my KEQ calculation. So these are the values that I need. Now one of them I already have, and I'm actually going to use the value that I have from the one that I extrapolated back to the origin. And so that concentration is equivalent to 0.00146 molar. Okay, and so that's the value that I got from there. That's why we set the calibration curve up in the first place, because we knew that when we had this mixture, there was no way of telling what the concentration of the ions was. So we needed some way of being able to figure that out. So from the absorbance that we measured, we've calculated then what the value of the concentration is on V. So this is going to be really the only one that I'm going to be using for all of these calculations. So in order for me to do this, I'm first of all going to have to work out the number of moles of the iron thiocyanate ions at equilibrium. So in order to do that, number of moles, name on your CV, equal to the concentration, which is 0.000146, and we're multiplying that by 0.004, and that's going to give us a value of 5.84 times 10 to the minus 7 moles. So that's the value that's going to go in here, 5.84 times 10 to the minus 7. The assumption that I'm going to make is that I did not have any iron thiocyanate ions in my initial solutions, so therefore their concentration is 0, their number of moles is 0. So therefore the change in order for me to get to this number of moles is the same number. Okay, so 5.84 times 10 to the minus 7. So that is the number of moles of this ion that has been produced during this reaction. Now, as I said, this is the one where we look at the mole ratios, which means these numbers are always the same. So 5.84 times 10 to the minus 7. Of course, they're always the same if the ratio is 1 to 1 to 1. If the ratio is 1 to 2 to 1, well, you would double that second value. But in this case, it's nice and easy, 1 to 1 to 1. So the problem that I have now is that whilst I add to 0, the change for the product, I'm going to have to subtract the change from the initial number of moles. So now I need to work out the initial number of moles of each of my original solutions. So in order to do that, I'm going to have a look at each of these initially. So my ions came from a solution which had 2 mil volume of a 0.001 molar solution. So again, the number of moles is equal to CV, which in this case is 0.002 times 0.001, which gives me a value of 2 times 10 to the minus 6 moles. So that's here, 2 times 10 to the minus 6. Doing exactly the same thing for the thiocyanate, SCN minus. Again, I had 2 mils, but this time I had a 0.01 molar solution. Another little thing you could look at here is to keep the molarities the same and see what sort of values you get. So again, N equals CV, which is 0.01 times 0.002. This one is going to be 2 times 10 to the minus 5. So I'm going to transfer that value back to my table. Up here, 2 times 10 to the minus 5. So now what I want to do is, in order to get down to these spots here, I just need to do some subtractions. So our first value is 1.416 times 10 to the minus 6. And our second value is 1.942 times 10 to the minus 5. So I'm now in a position to calculate my equilibrium concentrations for both the ion and the thiocyanate ion. So what I need to do again is use this particular equation, and I now have these two fractions sitting right here in front of me. So let me do those. So my KEQ is equivalent to concentration of products over the concentration of the reactants, which in this case, always worth writing it out in full. Good habit to get into, especially as you're approaching your exams. So let's substitute. So we've got this value, which is 1.46 times
10 to the minus 4 divided by this value, 3.54 times 10 to the minus 4 multiplied by 4.85 times 10 to the minus 3. And that gives us a value of 84.97. Okay, no units because that's the way that the equilibrium constant works when we can work out the units, but why bother? Now, I know that the value of the KEQ for this equilibrium are at around 20 degrees, so a little lower than room temperature, is around about 113. So I'm in the ballpark. And really, for an experiment like this, where we're using very small quantities, where small errors can be magnified, you could see that from my calibration curve just a slight difference there. If I redo those numbers, obviously there's a lot of processes to go through to get to these numbers, so I'm not going to do them today. But if you do redo the calculation, you probably end up with a value, I think, when I calculated it, around about 300. So there's quite a big difference between those two values. And this is one of the reasons why, we make sure that we repeat our experiments. It's very important that once we've got some data, we start to process that data, we repeat our experiments, and we think very carefully about how we're doing our experiments and what sort of errors might be creeping in. But overall, given this particular equilibrium and given the equipment that we've been using, I'm pretty happy with that overall result. Thanks for watching.